welcome to Alessandro Lavacchi. He's a senior researcher at Institute of Organometallic Chemistry of the National Research Council, Italy. He is also head of the electron microscopy facility. His research are focused on development and characterization of nanomaterials for electrochemical energy conversion and storage, with a focus on alkaline membrane electrolyzer and biomass conversion in electrochemical device. In his career, he co-authored more than 120 scientific papers and a monograph on nanotechnology in electrocatalysis for energy. Lavacchi is also chief editor of Coating, edited by MDPI, and editorial board member of Electrochemical Energy Review, edited by Springer. Alessandro will talk about a futuristic project for electrolysis of waste biomass. So Alessandro, the floor is yours. Start with your presentation, please.
Okay, thank you very much, William, for your kind introduction. Do you hear me well now?
Yes.
Okay, so I start sharing my screen now, and so we can begin the presentation. Okay. Okay. So the subject I'm covering today, it's a very novel one, and it goes in the direction of creating a nexus between green hydrogen production and the production of important raw chemicals for our society. The idea is to make both processes completely decarbonized, because it's true that the energy sector is for sure one of the most contributing to the production of CO2 and greenhouse gases, but on the other side, chemical industry is another very important contributor to these aspects. So lately, even the European Union has focused much on pushing for creating new technologies for making chemicals production entirely decarbonized. So at ICOM, that is my institute in Florence, we are working on this subject, and we started this activity more or less 10 years ago, when nobody was thinking about this possibility. And I must mention that at the beginning, what we did was pretty much not considered by the scientific community. There has been a big boost in 2017, 2018, when people started to realize that these electrochemical processes to combine hydrogen production and chemicals production could find an important place in the decarbonization of our society. Just to go a little bit more technical, I think most of you have had the chance to learn something about electrolysis. Electrolysis is just the process that splits water in H2 and O2, and it does this with electrical power supply. So this is, I think, the most relevant technology in clean hydrogen production so far, and the paradigm toward the complete decarbonization of the society envisioned by the Green Deal that actually fixed the target of completely decarbonized society by 2050 heavily rely on the production and the exploitation of green hydrogen. And this production is mostly by electrolysis, and the plans are to go to the terawatt scales by 2050. Well, this is for sure a big opportunity, but there are a few issues about deploying electrolysis at this scale. The most performing technology at the moment is polymer proton exchange membrane electrolysis that uses large amount of iridium, which is a very rare element and might pose a severe threat to the possibility of really deploying the technology at the terawatt scale. So, but by the way, apart from these, and many studies are going on to reduce the loading of these critical resources, electrolysis is a very solid technology that might be well considered for a massive deployment. Well, in our lab, 10 years ago, we decided to avoid the evolution of oxygen in electrolysis. Evolution of oxygen is a big issue for a variety of reasons. One is that oxygen is not a high added value product. So it's something we're gonna waste in most of the cases in air. And so we decided to cut this oxygen evolution and to replace it with the oxidation of biomass, means organic compounds and particularly alcohols. And these alcohols are extremely easy to be oxidized, much easier than water. So this in principle can cut very much the energy consumption of water electrolysis. So you see these two schemes here. On the left, you have the PEM electrolyzer with the H2 production and the O2 evolution, and on the right, you have the electrochemical reformer that oxidizes H2 and then oxidizes biomass, that reduce water at the cathode to produce H2 and oxidize biomass at the anode to produce this oxidized biomass. So if we use alcohols, in many cases, this oxidation may lead to the formation of very important chemical compounds with very high added value, and actually also bulk and raw chemicals. So it's something that has a huge potential to impact on the challenges for 2050. This is an example of what we can do with electrochemical reforming. So aside of the H2 evolution, if we use ethanol, for instance, from biomass fermentation, we have the opportunity to produce acetaldehyde and acetic acid. Acetic acid is produced nowadays with the Monsanto process or the Cativa process by Johnson Matthey. And these two processes are actually pretty problematic in terms of rare resources and also in terms of energy demand. So the opportunity to get these two compounds with an electrochemical process that works at room temperature and using basically known toxic compounds, it's I think absolutely very appealing. We are also exploring the possibility to use glycerol that we get from the scraps of biodiesel production, for instance. And with a variety of pretreatment, we can feed the electrolyzer to get chemical compounds of extremely relevant role in our society. And you see here, for instance, the acrylic acid, which is a very important monomer for the preparation of polymers. But on the other side, we can also get lactic acid, also very important for the fabrication of PLA. So that is a very good candidate, as a renewable plastic. So we have very many opportunities to get these compounds. Well, what is the technical performance of this device? Because we know that electrolysis is a very high intensity process for the hydrogen production. It works at 2 amp on square centimeter. For those who are not familiar with this quantity, 2 amps on square centimeter is truly a lot. So it means that just pretty small devices can produce significant amounts of hydrogen. So this is what we want to maintain, this high intensity, because it's the key for successful processes. And it turned out that from our experiments, electrochemical reforming is actually a very high intensity process that can compete with the state-of-the-art polymer electrolyte membrane electrolytic technologies. So if you see here, there are very interesting data. So if we consider the electrical energy input of the reaction that leads to the oxidation of these compounds and to the production of hydrogen, we see that compared to the conventional water electrolysis, we have an electrical energy consumption of 47 kilowatt-hour per kilogram of produced hydrogen, while we are more or less around 18, 19 with electrochemical reforming feed with ethanol, with the added value of the production of acetate in alkaline environment or acetic acid in acid environment. So basically, we have a recipe to to deploy this nexus between hydrogen production and chemicals production. From these curves here, we see that the energy input is extremely small compared to water electrolysis. Consider that the operating cell potential at even current density in electrochemical reforming is more or less 60% less than water electrolysis. So this opens up to a new business model for clean hydrogen, and which we mean not to be completely. It's not something that is going to substitute electrolysis, but it's something that might complement electrolysis. And the idea basically is that we can supply the biomass to the plants, which can be either relatively small. I'm sorry, this is a mistake. It's not 10 kV, 10 kilowatts. It's something less than 1 megawatt. So it's a small plant that can be close, for instance, to a refueling station that can fit trucks, for instance, and it's fed by renewable energy. So the model consider that we can obtain this H2 for transportation, and then we can collect the exhaust reformates from the electrochemical reforming, and then treat this reformate to get the chemicals. Then we can also deploy this technology in the context, for instance, of a biorefinery in big plants with more than 10 megawatts. And here we have, again, the opportunity to transform in situ this exhaust reformate into chemicals and to provide H2 for stationary and transportation use. What is interesting here is that since clean hydrogen is pretty expensive, with this model, we actually have the possibility to share the costs related to, I would say, CapEx and OpEx costs, not only in the hydrogen stream, but also in the chemical stream. So this cost sharing allow a decrease of the cost quota of the hydrogen, and might, in principle, allow to break the barrier of 1.5 euros per kilogram of produced hydrogen. Of course, this is a lab stage research. We are not quantifying TRL. We might say that we are more or less between 2 and 3. And there are many research actions to be carried out to drive this technology to a level where we can consider the possibility of a consistent exploitation. But indeed, there are many opportunities to do this. What is most important now is the energy return of the invested energy of the biomass we use as feeding for the system, because the higher the array of the biomass, the better is the system efficiency in storing the energy, the hydrogen energy, the energy in hydrogen. The other very important point, I think, is that this system might even operate at pressure higher than 350 bars, actually reducing the cost and the energy input of the compression stages for hydrogen. And there is also the need to work much on the chemical purification from the reformate. Actually, these activities are more or less ongoing, and we have a research proposal already submitted to the European Commission for evaluation that actually want to address exactly this question. The most important steps toward an exploitation actually are the analysis of the integration of the electrochemical reforming with the renewable energy production, because we know much about the behavior of conventional electrolysis when coupled with wind and photovoltaics, and still this is somewhat an issue. Then we must consider, I mean, the electrochemical reforming technology at light of the current regulation and the potentially future framework for hydrogen production, and even for the materials we use to fabricate the electrochemical reformer. I think one of the most relevant points is the analysis of the feedstock characteristics. I mean, especially the purity of the biomass derived compounds, and then also the flexibility toward different feedstock, because we might operate the system with different feedstock depending on the offer that the market has, and in some cases we might also use this system as a water electrolyzer, even if the feedstock is not available. Then we must, of course, work to integrate the process, of course, and both on the side of the feedstock and the products. So how to treat both. So what is the pre-treatment for the feedstock and the post-treatment for the products. And the other very important point we must pursue is the life cycle assessment and the social life cycle assessment of these new electrochemical technologies. So we have to work much on the side of the engineering now, scaling up the system to the scale of mole demonstrator, to make precise quantification of the heat and mass balances, energy and mass balances in the system, and also making consideration of what the final plant would like to be. So what components should be add to the system, and how we should operate it. Well, that's pretty much of the status of the electrochemical reformer. We have been working much in the last 10 years on this, and we published more or less 10 papers on the subject. I would like to put the attention especially on this paper of 2014, which should be here. It's number 10, because this was the first energy calculation on the system and demonstrated that under proper feedstock characteristics, this electrochemical reforming might be maybe more energy efficient than water electrolysis. And we started from that point, and we consider that eventually, using a biomass feedstock, we might reduce the size of the renewable energy plant that supply the energy for clean hydrogen production to the electrochemical reformer. This in comparison to water electrolysis. So if we consider only the electrical energy we supply to the system, we can consider that our renewable energy plant can be somewhat 50% smaller compared to water electrolysis at even hydrogen productivity. So that's the group that delivered this research in the last 10 years, and these are the most relevant collaborators and sponsors in the research we have performed. So thank you very much, William, for giving me the opportunity to deliver this talk. It's very important, I think, to start to draft the characteristic of these technologies, even in the context of the petroleum engineering, because I think we also need to integrate the competencies in those fields to be successful in exploiting these groundbreaking devices. So that's it. Thank you very much again.